Hey class, today we are going to talk about complex numbers, which is found in section 4-8, part 1 of your book. We're going to identify, graph, and perform operations with complex numbers. Alright, so just a little bit of review. So when you take the square root of a negative real number, that negative, if you take the square root of a negative by itself, it produces I. So for example, we have the square root of negative a, and that's really the square root of negative 1 times a. If you break them apart, the square root of that negative 1 is what produces the I, and it is no longer a part of the radicand, so that becomes I square root of a. Just like, for example, if we had the square root of negative 5, then it becomes I square root of 5. So in example 1, it says, how do you write the following using the imaginary unit I? So the first thing we need to do is find our factors of 18. So if I break down 18, 18 is 2 and 9 is 3 and 3. So the square root of negative 18 is the square root of negative 1 times 2 times 3 times 3. Now, the 3's are what will come on the outside. I'm left with the square root of 2 on the inside, and that negative 1, remember, produces I. So 3I square root of 2 is our answer. In try 1, we need to do the same thing. So again, break down your radicals if they are not perfect squares. So for example, 12 is not a perfect square. 12 produces 2 and 6 produces 2 and 3. So if I write that as a radical, that'd be negative 1 times 2 times 2 times 3. 2's are what can come out. 3 must stay under the radical sign, and that negative 1 becomes I, so that's 2I square root of 3. 25 is a perfect square, it's 5, so that becomes 5I as my final answer. So as we move on and start talking more about complex numbers, the first part, when you have the complex number setup of a plus bi, a, which is not attached to an I, is the real number, and then the number that's attached to the I is the imaginary part. And when you talk about complex numbers are real numbers, but they just have a specific setup. So if you look at the diagram, real numbers can be real numbers fully by just being a with no I. Okay, and then they can be imaginary numbers when they have the I attached to it, and then it could be pure imaginary when you only see the I. Okay, the most important part on this screen, however, is when we start talking about how to graph it. So the imaginary axis now becomes our Y, and the real axis is our X axis. So real by imaginary. So when we think X, Y, we think real by imaginary. And then to find the absolute value, of a complex number, you would just take the square root of both the a and the b squared. So the sum of the a and the b squared. So I know that sounds kind of complicated, so let's go ahead and look at it on the next page. So in example 2, we're asked to not only graph, but we're also asked to find the absolute value. So if we graph the first one, remember, it's real by imaginary. Okay, so the real axis says negative 5. So imagine that this is, our regular x-axis. So I have to go negative 5 to the left. And then it says 3 imaginary. So that's 3 towards the positive direction of the imaginary. So negative 5 plus 3i would be up here. Okay, and then if I wanted to find the absolute value, which by the way, if you're finding the absolute value, it basically just tells you the distance that point is from the origin. So that distance from the origin would be the square root of negative 5 squared plus 3 squared. So at this point, you drop the i's, you just talk about the coefficients. So that'd be the square root of 25 plus 9. And the square root of 25 plus 9 is the square root of 34. And so we're done. So we have our graph and we have our answer. So let's do the next one. If we have 6i, notice that is a pure imaginary answer. So remember, this is the real axis, this is the imaginary. We don't need to even put anything on the real, but on the imaginary, it is 6 units upward. So 1, 2, 3, 4, 5, 6. And so our answer is up here. Now that's pretty easy to figure out how far that is from the origin, but let's do it anyway, even if you can figure it out. So we would take the square root of, there was no real, right? So we don't put anything for the real spot, but the imaginary was 6 squared. And we know that the square root, 6 squared is 36, and the square root of 36 is 6. And that makes sense because this point here is 6 units from the origin, because I could go down 6 to get right back to the origin. So this is our answer. So just remember, the absolute value actually tells you the distance from the origin for complex numbers. Okay, so let's try the next problem. So 5 minus I, remember it's real by imaginary. So real is 5. So that's over here to the right. And imaginary is -1. So that means I have to go down 1. So right 5 and down 1 would be here. Now I need to know what that distance is for the absolute value. So that would be 5 squared plus -1 squared. 5 squared is 25, and -1 squared is 1, so that gives me the square root of 26. So that's our answer, that's our absolute value, and this is our graph. The last one, -3i, if I graph that, again, that's fairly simple because it's a pure imaginary. We should be able to do that in our heads, but if not, let's graph it. We're not dealing with any real, but we are dealing with some imaginary, and it's 3 units down. Now, that should be able to tell us that our final answer should be 3, but let's check. That'd be the square root of -3 squared, which gives us the square root of 9, which is 3. And that's what we expected because this point here is 3 units from the origin. In example 3, we are adding and subtracting complex numbers now. And so when we're adding or subtracting, first of all, with adding, you are just combining like terms. That is it. So the like term that matches with 3 is -2. So really that's like saying 3 plus -2. And then we need to combine our i's. So that would be, for example, 5i and 4i. So 5i plus 4i. So in total, our answer would be 1 plus 9i. And we're done. Okay? Now I won't follow those same steps on the second one because now we should be able to kind of match those in our mind. So 4 and -4, they're opposites, so they produce 0. So there is no real number here. Okay? Then I have -3i and +3i. They also cancel. So our answer here, for example 3, is going to be 0. The last one. Because you're dealing with subtraction, you need to go ahead and distribute the negative to everything in the second set of parentheses and then rewrite it. So really what we have is 5 minus 3i. Negative times -2 is +2. And negative times 4i is -4i. So if you combine your real numbers are 5 and 2, which give us 7. And then our imaginary numbers are -3i and -4i, and that gives me -7i. So 7 minus 7i is our final answer there. Okay, let's continue to practice this with try 3. So again, in try 3, we're just combining like terms. So our real numbers are 7 and -3, so that'll give us 4. And our imaginary numbers are -2i and +i, so that would give us -i. So 4 minus i is our answer there. Remember in the second one, because of subtraction, we need to distribute the negative. So that would give us 8 plus 6i minus 8 plus 6i. As far as real numbers go, 8 and -8 cancel because they are opposites. But then we're left with 6i and 6i. So 6i and 6i will give us 12i. All right, in example 4, now we're starting to multiply, okay? So for the first one, I know we haven't really talked about polynomials yet, but on the first one, we are going to distribute the 3i to what's inside. Now, one thing that you need to be sure that you know, because we haven't really seen it yet, is that, for example, the square root of -1 is what gives us I. But if I say I times I, which is I squared, okay, that gives me -1. Okay, so I could prove that if I go back. So if I prove this, that would look like, if I know that's I times I, so that means I would need 2 of those. So that's really the square root of -1 times the square root of -1. I could then put those under the same radical sign. And remember, that is a pair, and so that's what gives us -1. So that's this -1 here proves why that's -1. So again, all you need to know is that I squared equals -1. Okay, so let's go back to our problem. So 3i times -5 is going to give us -15i. And 3i times 2i, well, let's start with the numbers. 3 times 2 is 6. And I times I is I squared. Well, we can't leave it as I squared because we really know what I squared means. I squared is -1. So if I rewrote that, that'd be -15i plus 6 times -1. And 6 times -1 is 6. So if we put it in the correct format, remember it needs to be real plus imaginary. Okay, so that would be -6 minus 15i. That's just rewriting it in the correct format, meaning we put our real number first and then our imaginary. Okay? All right, on the second one, what I like to do on the second one is actually put it in a box. Okay, I'm going to put the second one in a box. It keeps it a little bit more neat and organized. So we have 4 and 3i, and then we have -1 and -2i. So in this first box, that gives us -4, and the one below it gives us -8i. In the upper right hand corner, that gives us -3i, but then the lower box gives us, well, 3 times -2 is -6, and I times I is I squared. All right, so remember, I squared is the same thing as -1. So really this is -6 times -1, which really equals +6. Now what I want you to recognize here is that your diagonals are like terms. So if I want to put it in the format of real plus imaginary, that would be -4 plus 6, which is 2. And then -8i minus 3i gives us -11i. And we're done. Okay, let's try that again with the second box just to be sure we've got it. So again, put this in a box. That's -6 and I, and then this is -6 and -I. So -6 and -6 is 36. -6 and -I is +6i. In the upper right hand corner, that gives us -6i. And in the lower corner, that gives us -I squared. Now again, remember, I squared by itself is -1, but really what I have is a -1, right? Because negative from the original part, and then I also have the -1 because I squared is -1. So double negative would make that +1. So remember, your diagonals are like terms. Well, the i's, the imaginary part, would cancel because they're the exact same yet opposites. So the only other like terms that are left are 36 and 1. So that gives us an answer of 37. Okay, let's try that on the next page. So again, for the first one, 7i and 3i, 7 times 3 produces 21, and I times I is I squared. But again, we know that I squared is the same thing as -1. So that will give us a final answer of -21. Okay, look at the next one. If we put that into a box, this is 2 and -3i, and this is 4 and 5i. If I multiply, this will give me 8. This is 10i. This is -12i. And the one below it is -15, but that's I squared. Now, again, remember, I squared is the same thing as -1. And negative 15 times negative 1 is positive 15. All right, if we combine our like terms here and here, remember, if you put it in the correct format, the real numbers go first. So 8 and 15 go first to produce 23. And negative 12i and positive 10i are negative 2i. And we're done. Okay, the last one, again, we want to put it in the box. So this is negative 4 and positive 5i. This is negative 4 and negative 5i. So in this box we get 16. Below it we get 20i. In the upper right hand corner we get negative 20i, and below that we get negative 25i squared. So again, I squared is negative 1, and negative 25 and negative 1 is positive 25. So just as a reminder, our diagonals are like terms. So in this case, those i's are gone. There are no imaginary numbers here. And we're left with 16 and 25. If you add 16 and 25, you get 41 as your answer. And guys, that's actually it with our presentation for today. So remember, if you have any questions, come see me for tutoring.